Hi, very good afternoon to everyone listening in, watching us, and warm greetings to the others who are joining us from the other parts of the planet. I'm Siddharth Pandey, and I'm very pleased to have with me Dr. Jonathan Clarke from Australia, Canberra, and the president of the Mars Society of Australia, which is a partner of the Earth and Space Exploration Program that will be taking place in Ladakh this year from June until October. Now, unfortunately, because of travel restrictions, we might not be able to have John over with us in India this year. But I should add that John has been the mind alongside my mind and many other minds, a few other minds, who has in fact been looking at Ladakh for almost half a decade now, more in fact, and trying and understand the importance of Ladakh from a Mars exploration perspective. And he's helped strategize and plan out some of the Mars analog research work, and some of it which exploratory work that we conducted in 2016 as well. And we have him with us today on this Sunday afternoon to talk about how he has built his career in Mars exploration, what has been his involvement with Mars analog research, what are some of the exciting things he's done and he's also doing right now. And for students out there who are looking to have a career in this field, we'll speak to him about what can they do to be a part of this project and how this project will really help them develop their careers in Mars research. So welcome, John.
Yeah, it's good to be here with you today, Siddharth, and everybody out there in cyberspace.
Thanks, John. And so briefly, John, talk us through your career. How did you go from being a general practitioner of geology, as you call yourself, into Mars research?
Well, a long and winding road, and I think like a lot of people's lives, sort of the pattern. The route you take is only visible in hindsight. So to go right back to the beginning, as long as I can remember, I've been interested in astronomy, in space, exploration. The earliest space mission I can remember was the Gemini 3 mission, the first Gemini mission, and I remember seeing it in the newspapers. And the very first space exploration mission I can remember happening was the Soviet Luna 9, the first soft landing on the moon, in 1966. I remember that very distinctly in the first pictures. And then, of course, getting on a bit, it was the Apollo program and the landings on the moon, Mariner 9 to Mars, Viking on Mars. And this all sort of framed the world I was growing up in. I grew up in Thailand. We didn't have a lot of media coverage, so most of what I knew sort of came in magazines weeks or even months after the event. But I read them very, very avidly. And I was really interested in astronomy. I was interested in any kind of science, really, but astronomy was what grabbed me. I really wanted to be an astronomer. But by the time I got to year 12 of school, the truth I finally had to accept was that I'd never be an astronomer because I just did not have the mathematical ability. And if anyone's out there who's interested in doing science, and people are saying, and you're not particularly good at mathematics, and people are saying, well, you shouldn't do science because you need to be a top mathematician to be science, don't believe them. You don't have to be what the school told me was I had to be a lawyer or a journalist or something like that because I was no good at maths. There are sciences out there to which, basic mathematics and arithmetic and trigonometry and that sort of thing is important, but you don't need some advanced maths to do many sort of sciences, particularly sciences like geology and field biology, the field sciences generally. So I decided when I was, 16, that I would start focusing on, perhaps I could go and look at the planet we live on, the star we live on. And instead of studying everything out there, I would study what was beneath my feet. And as a result, I went to university. I did physical geology, physical geography, I did some biology and philosophy as well, which were great fun, and ended up working in a mining company. But so ticking in the background was always this interest in exploring space, in Mars. I wanted to do Mars as part of my 4th year project, and my lecturer said, no, you can't do that. NASA's got that all tied up. They don't need input from some little Australian university. Oh, okay. So I studied the extinction of dinosaurs instead, the big impact that wiped out the dinosaurs 66 million years ago. People were just beginning to talk about that. So I was able to drag in planetary science there. And when I was working in the mining company, I was out in the middle of the desert, and everything was very red and rocky. And yes, I sometimes sort of imagined I was driving a Mars rover or climbing up a little hill on Mars to look at the rocks, as you do. We all have this story we are telling ourselves in our minds, or at least I do, and sort of imagine what this might mean in a different context. I find that very helpful because it helps you see the bigger picture and the significance, perhaps, of what you do. But different people might go about it differently. And over the next 20 years, I worked as a geologist in mining companies and exploration companies. I did a PhD working in the northern Flinders Ranges, studying fossil reefs. I worked in a mining town looking for gold and nickel in some very ancient rocks that were over 2.5 billion years old in Western Australia. Later on, I worked in the Philippines, in Chile, in the Atacama Desert. Now, there's a very Mars-like landscape. But always sort of in the background, how would we go to Mars? How would we explore Mars? What was coming from Mars for the missions? And remember that after Viking, 1976, when I was still in high school, right up to 1996, which was near the end of my time with a mining company, there were no Mars missions, except for one Russian mission that orbited for a few months until something went wrong and we lost contact with it. And so there was very little new information, and we were just sort of chewing over the same data and wondering what it meant, like chewing over an old chapati that's too chewy to swallow. It's just sort of sticking in our mouths and in our minds, and we couldn't really go any further. But in 1996, new missions started, the Pathfinder lander on Mars, the Mars Global Surveyor, and suddenly all of these fantastic images of the Martian surface started pouring in and revolutionizing what we knew about the surface. I paid attention to that, but it wasn't anything that touched me. But unbeknownst to me, in America, someone called Dr. Robert Zubrin, an aerospace engineer and activist, had started up the Mars Society in 1999. And in 2001, an Australian Mars Society started. And I was then working at the university, the Australian National University here in Canberra, and I was surfing the internet, as you do when you're at work, in my own time, of course, but I was at work. And I came across Mars Society Australia. I thought, is this some sort of cult or something? But I thought I'd have a look. And they were advertising for someone to lead a field expedition to Central Australia to look up potential sites to build an analog station. I thought, I can do that. So I rang up the contact person, who was Guy Murphy, who Siddharth and I both know. And he assured me, no, this wasn't a strange cult started by Robert Zubrin, but they were really keen for people on the ground, or ordinary people, to get involved with the goal of humans on the red planet. So I went on the expedition. We traveled all over Central Australia. I met some fantastic people, all of whom are still friends with me now, most of whom are still actually active in the Mars Society. James Waldie, for example, Guy Murphy, Graham Mann, and a number of others. And we found a site in northern South Australia that we thought would be an ideal place to focus our Mars analog researchers, a place called Arkaroola at the top of the Flinders Ranges. Shortly after that, I ended up being elected to the board, and I've been part of the board of Mars Society Australia ever since. 20 years this year, a long time. And what has that led to? Well, I've still been working as a geologist. I mean, after I finished at the university, I joined the government organisation, Geoscience Australia, working in environmental geology. But on the side, I was doing Mars analog research, because through the Mars Society, we were able to go on expeditions to areas in Australia, to the Mars Desert Research Station in Utah, where Siddhartha's been as well. It's a simulated Mars base, but you can go and live in for weeks and months at a time out in the desert of Utah, in a beautiful red barren desert with huge huge mesas rising up like a Western movie, an incredible landscape with many, many similarities to what we would expect to find on Mars. And I've been there, I spent 3 months there, 4 months there in total, no, 5 months there in total on various expeditions ranging in from 3 months down to 2 weeks. Doing all sorts of things, studying geology of Mars, or studying the geology of that place and comparing it to Mars. Being a guinea pig for engineers and psychologists. So I lost count the number of times the engineers killed me in a simulation. I'd be driving a rover or walking around wearing a simulated spacesuit, and something would go wrong and I'd die. So you get used to that when you do Mars analog research. And that led to doing other work of this type in northern Canada, up in the Arctic, at the Mars Arctic Research Station, visiting places like New Zealand, and also back in 2016 to Ladakh, which is perhaps the best place in India to carry out Mars analog research of certain kinds. It's a unique place, not only in India, but in the world. It's a high altitude, cold desert. And in that regard, it has many similarities, not so much with Mars now, but how Mars may have been 4.5 billion years ago, when things were warmer, wetter, and there may have been small amounts of oxygen in the atmosphere, and certainly there were bodies of water, lakes and rivers active on the surface. So that's what's brought me here. And then Siddhartha's very kindly invited me part of the team at Amity University, and been working at Kutch and at Lonar Crater in the center of Maharashtra, and it's all been happening from there. That's my story.
Thanks, John. That's the first time actually I heard a few things as well. I never knew that Guy, in fact, was the one who was the first person you reached out to.
yeah, it's all his fault.
No, that is terrific. And I think the essence of the Mars Society is something that we really would like to imbibe in Earth Space Exploration Program as well. That it's not just exploration and adventure and pursuit is not just for those who are working in space agencies or are wearing lab coats and working in laboratories, but it's something that each and everybody can be a part of that endeavor. And the society in the US and in Australia has been doing that so well in terms of incorporating people from different walks of life to come in and work together on projects. And that's something that we really are working towards as well in India, where we're able to get people together and work. So let's talk a little bit about the next challenges for human exploration. We've had astronauts walk on the surface of the moon. How much have we learned from that, and how much does that help us prepare us for Mars? And what kind of support do we get by doing work at analog sites for that?
Yes. Can we learn from the Apollo program? Well, I will sound like a politician. I will say both yes and no. The Apollo missions to the moon, the 6 successful landings and the 3 orbital missions, 9 in all, were some of the greatest achievements of the human species, and certainly one of the greatest exploration endeavors so far. And there's a lot we can learn from that. The issues of doing field science or wearing spacesuits, working remotely from Earth, working in a very hostile environment. All of this, and a lot of the technology can be transferred from the Apollo program to going to Mars. Of course, very updated. Your mobile phone has far greater capacity than the computers they used in the spacecraft going to the moon. It also says it's something perhaps that you don't need necessarily the most sophisticated technology to do the task. You need the right technology for the task. And that may often be something really simple and really straightforward rather than something that's very, very complicated. But in other ways, going to the moon with Apollo is very different than going to Mars. So for a typical Apollo mission, they blast off from Earth, and 3 days later, they'll go into orbit around the moon, and then the following day, they'll descend to the lunar surface, 2 astronauts in the lunar module, and they'll spend up to 3 days exploring the surface. Then they'll descend back to the command module, join their colleague who's been sitting there by himself, and a day or so after that, spend 3 days coming back to Earth, less than 2 weeks away. When we go to Mars, it'll take a minimum of about 6 months to get there. And it'll take 6 months coming back. How long you spend at Mars is really what defines how worthwhile it is. So you'll want to spend as long on Mars as is practical. And that's about 18 months. You actually have to wait that long for the planets, the Earth going around the sun, Mars going around the sun a bit slower, for them to line up first so you can go, and then you've got to wait for 18 months till they're all lined up again so you can come back. So you've got 18 months to explore, and the challenges of exploring Mars for 18 months are enormous. So on the moon, they wore a spacesuit, or they wore spacesuits, of course, or moon suits. Only had to wear them 3 times per person, because they only did 3 excursions out to the lunar surface, 4 in one case. Going to Mars, we'll be spending 540 days on the Martian surface. Even the most conservative program would suggest that you'd probably be going out every other day, or at least every 3rd day. So there will be excursions onto the Mars surface, well over 150, perhaps even 200 of these excursions. And that has a huge impact on planning, on the robustness of the spacesuits. It's one thing to build a spacesuit that can last for 3 days, build one that will last for hundreds of excursions onto the Martian surface. How do you service it? How do you maintain it? Can the astronauts work at that level of intensity? How will they work? The Apollo astronauts never went more than about 4.5 kilometers from their lander. They walked perhaps 1 or 2 kilometers away. It's the most extreme example. Further trips they took in a little electric buggy. But when you're on Mars, when you've got 540 days to play with, you may well be using a big pressurized vehicle. It's the size of a medium army truck, which has got everything in it you need, and they go out that for 2 weeks at a time, traveling 100 kilometers away. Imagine what it's like to go for 100 kilometers away from your only other source of food or water or of oxygen, of shelter. It's going to be a very strange experience and a very demanding operation. But if we want to explore Mars, we've got to get used to doing that and to get it right every time we do it. We don't want to leave bodies on the surface of Mars if things go wrong. So we learn from Apollo, but we also have to learn things from Mars as well. And that's why we do the analog research. During the Apollo program, all of their EVA activities, they tested out with people wearing mock-up spacesuits. Going to Meteor Crater in Arizona, which is a little bit like Lonar, but smaller. Going to volcanic areas in Hawaii, and testing out their handheld equipment, testing out the little electric rover, testing out how they'd work with spacesuits, learning all the knowledge about geology and EVA procedures beforehand. And one of the things that we can do in places like Ladakh, in places like Lonar, is we can is people can go out and they can start testing the instruments, testing the procedures, perhaps testing the suits. And if we develop places like Ladakh properly and people become aware of it in the international space community, I'm no doubt at all that future astronauts, including those who will walk on Mars, will come to Ladakh, will come to Lonar to learn about the geology and perhaps practice their operations. Just like we have had future astronauts go to the Mars Desert Research Station in Utah, where you and I have been, to start learning the skills that they can then apply in the astronaut program.
Thanks, John. I think that sums up quite well the importance of analog sites. Now, let's talk a little bit more about Ladakh in particular. Now, we were there together in 2016, and we explored particularly the southern region of Ladakh, near Sokar and Poga. And from a scientific perspective, there's several things that we have identified that we would like to get. We've seen that there's hydrothermal activity. There's a hot spring in Poga region, which is exciting for astrobiologists. An hour's drive west from there, there is the saltwater basin of Sokar, which is connected to that freshwater lake, Stars Bukso as well. And alongside both these lakes or the wet basins, we see a lot of permafrost exposed layers, those mounds that we have seen, and then there's permafrost that's also within reach to study. So from a scientific perspective, that region, of course, offers a lot for us to learn and test our scientific equipment. But if we were to conduct some human-centric operations where we'd like to test the performance of future Mars astronauts, so what kind of projects do you envisage that can be implemented in which the science alongside the human exploration can be developed for Mars?
Well, there's many possibilities. One of which is how to use tools such as drills or various ways of excavating, perhaps a little electric excavator, or even astronauts in simulated spacesuits and shovels, of how to access the permafrost. I mean, scientists on Mars are very interested in permafrost because it may preserve evidence of ancient life. But how are you going to get that? How will you dig down to that? It may be meters below the surface. So how do you do that excavation? How do you sample it without contaminating it? Us humans have rather dirty bodies. We're constantly shedding. Even when we're in a spacesuit, we are shedding little bits of skin, bacteria, various chemicals. It sounds gross, but that's a reality. And a spacesuit is like a big balloon, and it will leak. So how do we sample these very pristine environments while wearing spacesuits? That's a challenge that we can test while working in somewhere like Sokar or the other areas in the Ladakh which have permafrost. Another thing that we can test is how do we map ice? Ice is not only important on Mars scientifically, but when we go to Mars, every kilo we take to the surface of Mars will cost certainly tens of thousands of dollars, and more likely hundreds of thousands of dollars to take from Earth and put on Mars. So every kilo we can not take, is money that we don't have to spend. And one way of doing that is learning how to live off the land. So when we fly to Leh, we don't bring all our food with us. We don't bring all our water with us. We don't provide our own power, with batteries or whatever. We use what's available there. We go out to a restaurant. We get water from the tap. We you plug into the power from the mains in our room. We live off the land in that sense. And when we go to Mars, of course, there's no town we can live on. But if we need water, we can perhaps extract it from the permafrost. It's just ice. if we can get water, we can make propellant to bring us home again. And that's going to be save potentially tens and maybe hundreds of tons of mass that we don't need to take to Mars. Of course, we all use water. We all use roughly 12 liters of water per person per day for drinking, for preparing food, for washing, and for keeping it where we live clean. And this is something we can test in a Mars analog station. But if we can find that water on Mars, that's water we don't have to take. And of course, out of water, you can also get oxygen to breathe. That's something else you don't have to take to Mars. But how do we find ice? If it's beneath the surface, how do we look for it? Particularly if you're wearing a mock-up spacesuit. So we can test various types of geophysical equipment like radar or electromagnetic instruments or conductivity and resistivity mapping to map the areas of ice that lie beneath the surface and see how effective these would be for working on Mars. But it doesn't stop there. One of the big challenges of going to Mars, as I've said, is we're going to go outside a lot. Maybe every day, perhaps once every 3 days, but we're going to go outside. On the International Space Station, when they want to go and do their EVAs, their extravehicular activity, their spacewalks, it takes anything up to a day to prepare for that. And part of that is because the International Space Station is pressurized at sea level, like in Mumbai, with a mix of nitrogen and oxygen, just like ordinary Earth air. But when you go out in your spacesuit, you drop your air pressure down to a third of that, and you're breathing pure oxygen. And if you just went straight from one to the other, you'd get the bends, just like divers do if they stay down too long and come back up. And so there's a long, complicated procedure they go through to prepare themselves physically for going out of the space station. Now, that's fine on the International Space Station, where they go out on average once every 2 months, which isn't very often. But on Mars, they'll be going out, like I said, perhaps every day, certainly every 3 days or so. We can't afford to do it that way. So we need to change the atmosphere in the station. Probably not to pure oxygen, which is what they did in Apollo, because there's issues like that, like fire and so on. But there may be other pressures. Perhaps we can start at a much lower pressure, like we have in Ladakh. I mean, if you lay, the air pressure is, which is at 3,500 meters, the air pressure is about 2/3 what it is at sea level. And hundreds of thousands of people live there quite happily. Maybe we can actually have our station pressurize that, or at SOCAR, which is just over half 1 atmosphere pressure. But a lot of medical doctors, space medical doctors, are worried about low pressure. If we take people to Ladakh or work with the local people, we can see, well, how are they coping? How are they coping carrying loads, climbing mountains, walking around, doing complicated tasks with machinery, with equipment, doing science, with that in that low pressure environment? Is it something that we can then take back to the design of our Mars stations? And so rather than being pressured to sea level, somewhere like Mumbai, we can work at a much lower pressure, like people do in Leh or at SOCAR. And that has other advantages, because the lower the pressure inside the station, the less oxygen you need to take. The lighter your structure has to be, because it doesn't have to be as strong to keep that pressure in. And also, the lower the leak rate, because the higher the pressure inside, faster the air will leak out through all sorts of little cracks, which we can't avoid. So you keep the pressure lower, there's multiple advantages. So that's just some ideas.
Great, John. I think things we follow up on each of those. Let's move into question answers, because I'm seeing a few interesting ones come in. So Suriendu, he's a popular name now. He's already signed up for one of the. He's quite excited and enthused about the upcoming activities. So he asks, hi, Dr. John, you just told us that you've been in Atacama Desert. I don't believe you have, though, John. He did mention that.
there's not much I can say to that, except I've got the pictures to prove it. I've got the rocks on my mantelpiece to prove
Oh, you
it.
have. I'm sorry.
Yeah.
I'm sorry. I missed that. I thought you hadn't been there. Okay. Sorry then. My bad.
I have been. Yeah.
You have been there. So my
Yeah.
apologies. I thought you hadn't. So he asks, what are the similarities out there in Ladakh with respect to Atacama? And what are the potential microbes or microfossils that you expect to find on Mars? So those are two questions. Let's start with.
That's a very good question. The Atacama Desert looks very different to Ladakh. I mean, there are similarities. It's quite high. The Atacama Desert starts at sea level, and then it goes up to a plateau, which is at about 2,000, goes over a range, which sort of goes up to about 2,000 meters, and then there's like a valley, which is at 1,500 meters, and then it goes up through another range to a higher plateau, and then up to what they call the Altiplano, which is about 4,000 meters, similar to sort of SoCal. It is really, really dry. It has even less rainfall than Ladakh. Antofagasta on the coast has, from memory, about 4 millimeters of precipitation a year. Not rain, precipitation. A lot of that is actually from dew in fogs that come in off the sea. So it's dry. I remember being in a hotel room in Antofagasta and looking out across the roofs, flat roofs, of course, because there's no rain, and seeing there are holes in people's roofs with bits of cardboard on it. Now, it's quite a wealthy town, so it's the cardboard on the roof isn't because they can't afford to fix their roofs, but that's all you need to do. You just chuck a bit of cardboard on and it keeps the dust and the sun out. And a few years ago, they had a heavy rainstorm in Antofagasta, and all the roofs leaked because all the cardboard went soggy and the rain came in. So it's incredibly dry. There are graves out there that you can visit around some of the towns, and the people who are buried there are all mummies. Not because of any chemical process that's been done to them, it's just that everything's dried out. It's very, very creepy. So it is drier than Ladakh. It's dustier than Ladakh. So a lot of the hills are mantled with sort of like a smooth layer of wind-blown dust and sand. So a bit like icing on a cake, except it's sort of a reddish brown, like Mars. So in that respect, it's very, very Martian. When you go further up, you start running into hot springs and snow-covered mountains and glaciers and permafrost like you do in Ladakh. There are salt lakes with flamingos, like you see in some parts of India. And there are volcanoes, which fortunately we don't get in Ladakh. But, you go to the Atacama Desert, and on a clear day, sometimes you can see 5 or 6 volcanoes all smoking gently. Very, 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 very cool. So there are similarities. They're both high, or in part they're high. At the Ladakh is always high. Parts of the Atacama are high. They're dry. The Atacama more so. There are salt lakes there. Everything's brown and dusty. But the differences are there are volcanoes in South America, in the Atacama, which we don't have in Ladakh. The mountains are mostly not as jagged as a result, compared to the incredibly rugged volcanoes in Ladakh. The salt lake chemistry is often quite different. So the salts, the soils in the Atacama Desert are full of weird nitrate and iodate and perchlorate salts, which we don't see in Ladakh, which instead we have sodium-rich and sulfate-rich soils. So that's different. Microbes on Mars. Well, we don't know if there are any. This is one reason why we want to go to Mars, to find out. I mean, everybody's interested in life on Mars. Maybe there is, maybe there was, or maybe there wasn't. And each of those 3 answers is very, very interesting. If there was life on Mars, what can that tell us about how it appeared, and what does that tell us about how it appeared on life on Earth? If the life is still there, how does that compare with the microbes that live in hostile environments on Earth, in hot springs, in very salty soils, at high altitude, within rocks. And if there is no life on Mars, why not? Is it that Mars is too small? It's just too small. There's not enough air. There's not enough gravity. There's not enough something, so it never appeared. And that's going to be very important scientifically as well. And we can then say, well, if there is no life on Mars, how does this affect the processes that go on? So on Earth, we go outside. If you've got a garden, go to the garden. If you haven't got a garden, go to a park. It doesn't matter where you are. Everything that's going on there, the interaction between the atmosphere and the water and the soil and the rocks, all passes through microbes and larger animals and plants. If there is no life on Mars, those same processes or similar processes still be happening, but they'll be happening without anything coming, any role of microbes. So will they be faster? Will they be slower? Will they be different? Will there be new processes that we don't see on Earth? Or will there be processes that they don't get on Mars that we have commonly here? We will learn a lot about planetary processes and biological processes if we have an environment that hasn't got any life. And of course, if there is any life on Mars, that will make the human exploration of it much easier as well, because we won't have to worry about the potential of contaminating, spreading Earth bacteria on Mars, although I think that's very unlikely, and even more unlikely, bringing life back on Mars that will turn us all into flesh-eating zombies or whatever. Not, I think that's at all likely either.
Yeah. So there's always a certain sense of discussion between people who are pro human exploration and those who feel that robots are enough. And I know you've spoken a lot about this, but perhaps for the benefit of the audience, can we just point out why is it important to have humans on the surface of Mars for exploration?
Yeah. Robots are very, very important. First of all, they're a lot smaller. So they're even a big robot like the Curiosity rover weighs almost a ton. But that's much, much smaller than sending a group of astronauts to Mars in a spacecraft or a series of spacecrafts that might weigh between them 50 or 100 tons. So it is easier and cheaper to send robots. And robots then make great pathfinders. They can go to Mars, they can measure the environment, they can tell us what's there, they can show whether or not you can drive across the surface, if there's any hazards on the surface, they can measure radiation and temperature and so on. So they're very useful as pathfinders. There are also tasks that robots are very, very good at. Boring tasks. So for example, we all know that there are hundreds of satellites orbiting the Earth, watching the weather. From many countries and many organizations. India has weather satellites. Europe has weather satellites. China, Russia, Brazil. They all have satellites monitoring the weather. Nobody in them, because sitting there watching the weather go past would be very, very boring for an astronaut. So it's all done by robot, by machine. And there are other things like monitoring earthquakes. We have many parts of Earth. We have automatic seismic stations, automatic weather stations, simply because it's easier to do that automatically than having a human sitting there watching it. And the same on Mars. But there are many, many tasks where people are better. So I've got a glass of water here. I can reach out and pick it up, have a drink, put it down. Now, a robot doesn't need a drink of water, and if it did, it would fry its electronics. But to get a robot on Mars to do something simple like that, like picking up an object, doing something with it and putting it down, would take a day. They are incredibly slow. That's partly because of the time lag to take things to Mars. That's partly because of the fail-safes, because if you've got $1 billion machine, you don't want anything to go wrong. So if there's any difficulties, you want it to stop rather than pour water down its electronics or whatever. it's also the fact that the way robots work on Mars is the commands are sent first thing in the morning. The robot does its stuff, like, you know, pick up a rock or drive 10 meters or take a photograph. And then at the end of the day, it radios back to Earth whether or not it's actually done that. And something might have gone wrong in the first 5 minutes and it might not have done anything. But people still won't know to the end of the day, in which case people all over the world will be scrambling to work out what went wrong and how to fix it so they can try again the next day. And of course, if it worked, then they'll be scrambling to work out what they want to do next. So it is incredibly slow. The average speed, this includes both stopping and doing science and driving, of the Mars rovers, all of them, has been between 5 and 10 meters a day. Now, when we send people, you know, an astronaut, like, you know, can pick up a rock and put it down again in seconds. An astronaut can walk at, you know, several kilometers an hour. If they're driving, you know, they might drive at 15 or 10 kilometers an hour. In a day, they could drive 100 kilometers and visit a whole new site. As humans, we can work in real time. We can work faster and much more dexterously. You know, we're just much better at picking things up and doing them. A friend of mine who worked with robots said, you know, you can get a robot, you teach a computer or have a computer program that can play chess better than anybody else in the world, any human being. But it's very difficult to get a robot that can actually pick up the pieces and move them the way a 3-year-old child can pick up a chess piece and move it. And they can just do that almost, you know, without thinking. You know, you tell your daughter, your granddaughter to pick up a chess piece and move from here to there, and they'll do it. Right? Get a robot to do that. That's quite something. So robots that do that sort of precision work in factories where they're doing the same thing over and over and over again. You know, they're not out there picking up rocks in a desert where no one's seen before, except on Mars. And that's why it takes days and days and days to do something. It takes an hour. It would take an astronaut 5 minutes. Of course, astronauts, like I said, will work on Mars in real time. They won't have to wait for a time delay. They won't have to wait to be told once a day what to do. And if necessary, they can cheat. That sounds funny. But there was a case in the Apollo program, Apollo 15, when they were driving back from one of their excursions. Mission Control said, you know, go straight back. You know, everything's running a bit low. We're running a bit behind schedule. Don't stop. And then Dave Scott, the commander, saw just in front of them, come as they're driving along, a really interesting looking rock, which he thought should be brought back to Earth. So what did he say? He said, oh, I've just got to adjust my seatbelt. So he stopped the rover, undid his seatbelt, picked up the rock, put it in the bag, and then did his seatbelt up. And that's now known as seatbelt rock, right? People are creative that way. Now, you don't want to do that too often because things might go wrong, but it shows the sort of ingenuity and creativity that people can do. And that's another thing that people can do is we've got eyes, we've got imaginations, we've got that inside us that makes us human. So we can take in Mars and we can create art. I mean, the very first person to walk in space, Alexei Leonov, was an artist. And even he was only in space for 2 days for that trip, and very, very busy. But he did an artistic work of the first sunset he saw in space. Al Bean, one of the Apollo astronauts, after he came back, he retired from being an astronaut. He became a very famous space artist. Others have become writers. I mean, poetry, philosophy, imagination. No robot can do that, but by going to Mars is seeing a whole new world, seeing our Earth as a little dot in the sky, a little star in the sky. No robot can do that, but for those emotional and philosophical and spiritual dimensions, you know, we need people.
Great, John. I think you have summarized that perfectly and made a very strong case for humans on Mars. Let's quickly get through some more questions that are specifically about Ladakh. So I'm just going to prioritize and restructure. Says that during the online course,
Sorry, you're
at the
breaking
best.
up. Then.
Can you hear
Could
me?
you ask that again? You were breaking up.
I will. Can you hear me?
Yes.
Okay. The question is, hang on, let me see. Yes. So Ladakh is not really a site which is less visited, of course. It's a popular tourist destination.
Yeah.
You know, the anthropogenic activities in Ladakh, how do they affect some of the activities we want to do in Ladakh?
Yes, we'll need to pick our sites carefully. And there's sadly some of the really good sites there, like the hot springs, are quite severely impacted. So we'll need to work in areas either where there is minimum anthropogenic input or where we can characterize that carefully so as to see past it or look through it. And Sokar, where we want to put our station, is one of those sites. Also, by perhaps highlighting the damage that some of these other areas have experienced, we can bring to people's attention the importance to preserve them and to, in fact, undo the damage. We often look at environmental damage and say, oh, that's terrible, it's ruined forever. But often it isn't. You know, we can undo the damage that we do. And I know that from my own experience. So a number of years ago, I went to New Caledonia, an island in the Pacific. And we took a group of students from ANU, they're geology students, and we're looking at the coral reefs there. And there was one particular island just off Noumea, the capital, called Duck Island, Île-aux-Canards, if you're French. And beautiful coral reefs. You have masses of fish, more fish than you could poke at, and lots of sea snakes. It was a wonderful place. But 40 years ago, that place had been totally destroyed by ships anchoring there and destroying the coral, people throwing dynamite into the water to kill the fish, to collect it. All the coral was dead. There was hardly any fish there. But by making a marine preserve, gradually over the years, the coral grew again, the algae came back, the fish came back, and now you wouldn't know that it had been damaged like that. And I'm sure the same can be true of these heavily impacted places like the hot springs. You know, you control pollution, you perhaps control the number of people, or you control where they go and what they do there, and perhaps remove some of the buildings and so on that impinge on it. But that's not just for us, that's for people who live there and the wider community and the government, to talk to the scientists and the people who want to study it to see which way they want to go. Because we can't always return something, although even if we can return something to what it was before, we might not always want to because it's too useful. So, for example, if there was a electricity station on this hot spring, right? You know, that electricity is important for the local community. So you might not want to return that hot spring to its original condition because it's too important change. Just like you wouldn't turn a rice field back into jungle because people depend on that for their livelihood. So they're complicated questions, but it's an important one. And I know, you know, when we were at Kutch, when we were at Ladakh, when we were at Lonar, we were talking about these sort of issues. Hope that makes sense.
It does, John. That's a great point that needs actually to be addressed separately, where we talk about the preservation of these sites. Yashraj asks, what led to Sokar Lake being salty now? You know, we spoke about this specific lake, the wet basin now. It's no longer classified as a lake because of the evaporation. So the question is, what has led it to be so salty? How different is salt at Sokar from regular sea salt? Is there any possibility of finding sodium chloride salt on Mars?
Okay, three very good questions. All right, salt can come from two ways in a lake. All lakes contain at least a little bit of salt, even a freshwater one like Pangong salt. Some of that salt comes from the sky. If you go to the sea and there's waves breaking, you can see a haze sometimes from the sea spray. And when that spray evaporates, it forms salt particles. And those salt particles can be transported for hundreds of kilometers, thousands of kilometers, particularly in a dry climate, until they eventually settle out as dust, or they get brought down to the ground by rain. So, for example, where I used to live in Western Australia, there was a salt lake called Lake Lefroy. And when I looked at the numbers for the salt in the lake, by the way, was identical to sea salt. I worked out that every year, 5 tons of salt per square kilometer was deposited there by rain. So rain and dust from above can be a very effective way of bringing salt into a lake.
So perhaps some last final comments from you, John, in terms of how such a program can help the student who is probably at the crossroad of deciding whether he wants to enter into a STEM field or continue a research career, and B, for a regular traveler. So what do many of these things, because people tend to get very intimidated when they see a lot of heavy scientific terms and research happening. It kind of scares them off. So how do we ensure that they don't get scared off and try and help them find inspiration and probably connect with what they're doing in their regular walks of life and feel inspired about the whole journey?
I can only speak from my journey. I'm someone who likes the big picture. That's why I did biology and geology and geography and philosophy as a student. A lot of schools, a lot of universities try to sort of put you into a very narrow, specialized stream, and there's a place for that. But even if people go into a narrow stream, please try and keep that bigger picture. So, for example, if you're looking like I was for copper, for a mining company, doesn't mean to say you can't think of, well, what would these rocks look like on Mars? Yeah. Perhaps think about what people might do with the nickel or the copper that you find. Always think about the big picture and the impact of what you do might have on the local community and so on. So always think of the big context. Secondly, all the analog research, Mars analog, Moon analog, Venus analog people have always come into it from doing something else. In my case, it took a long time. Hopefully for the people coming on this course, it won't be as long for them. But get as good a grounding in chemistry or geology or biology or engineering or human factors that you can. So you can bring that and you can know how to apply that to problems related to Mars or the Moon or Venus or wherever. The second thing is, or I think it's very important, is to be flexible. I'm a geologist and I became a guinea pig for the engineers and for the human factors people. Yeah, be prepared to work with other people and not just do your own stuff. Because when you go to Ladakh, those of you who are going, you've got the incredible fortune of doing that, you will be working as a team and you will working together, and what you do as a team will always be more important than what just you do for yourself. Don't be afraid to learn new things. As I said, I learned, to my amazement, about psychology and engineering. And you never know when that knowledge might come in useful. Work as a team, achieve as a team, and perhaps the most important thing is whatever you do, have fun. I mean, I remember a few years when I went to Ladakh, it's just gobsmacking, as we say in Australia. You're sitting there and there's these amazing mountains. You're at an altitude of 4 kilometers above sea level and the mountains go 2 kilometers higher than you. There's not many places in the world where you can do that, where you can see that. There are these weird salt lakes. They're not boring salt lakes like in Australia, which are sodium chloride. They're sodium sulfate. Yeah, the hot springs, they're not boiling like a kettle on a stove in Mumbai at 100 degrees. They're boiling at 80 degrees because the air pressure is so low. There's all the strange animals, the marmots, the yaks, the wild donkeys, the kian. And there's a whole human landscape of different people living in different ways, doing things. You've got those of you who are going, it's going to be maybe a once in a lifetime opportunity, hopefully not, but you will see and do things that you never thought yourself possible, that you never thought that you'd ever see. So have fun. May it enrich your lives from here on.
John, I can almost sense your feeling that you're not able to come to India this year.
I am very green with envy. Next year.
So, absolutely. I should add that John is going to be a constant throughout this journey. He will be working with us remotely to help coordinate some of the scientific activities and also help plan out some of the Mars mission simulation work for next year, for 2022. And unfortunately, we've run out of time today. We've had a lot of other questions, which we are writing the responses in comments as in when we can, hopefully within today itself. So John, once again, thank you for taking out time and spending your energy and thoughts with us.
Thank you.
More and probably do a panel discussion next month. It will be a larger group of people from different areas, and we'd definitely like to have you as well and do a joint panel discussion, members from other regions who are also coordinating, or maybe some of them potentially visiting India this year. Dr. Sudha Rajamani from Indian Institute of Science, Education Research, Pune, joining us. We'll be confirming the time, and the post will be up and live, I think, by Tuesday as well. So we continue our series of live Q&As to help students and explorers learn more about some of the activities we're doing, and stay tuned for more information. And for those of you who haven't done it already, the registration page and information will be visible after we end this call and also in the post description. So I look forward to inviting you and seeing you in Ladakh in the next few months as well. So thank you, John.
Thank you.